Ladies and gentlemen, so we will start our first session of the IMO showcase. So let me just tell you for a couple of seconds about these. Maybe I talked about this to the leaders, but I didn't tell to all of you. So this year we decided to introduce the so-called IMO showcase lectures. So basically, each instructor at the camp will present an IMO problem, will dissect an IMO problem in his own style. And each lecture will have 40 minutes plus 5 minutes questions. It will be very interactive, hopefully, and it will be open to all of you. This includes students, leaders, instructors, and anyone who wants to attend them. So today we will have two IMO showcases. Each showcase will have two teachers. So two instructors will present problems. So 40 minutes plus 5 times 2 is 1 hour and a half. So today we'll have two of them back to back. And it is my great pleasure to introduce our first speaker for today, Stijn Cambie from Katholieke University of Leuven. From Belgium. Probably all of you know him already. He has been here at the camp. This is his third year. And let's welcome him.
Thank you, everyone. So I wanted to present a famous IMO problem, but I hope it's not too famous, since then this talk might be less interesting for the ones who know. But so I will speak about the famous windmill problem from 2011. And before introducing you to the problem, I first want to give you a slight idea about the scores. So in 2011, there were only 6 people who solved the problem 6, which is usually the hardest problem of the IMO, so not so surprising. But the problem 2, which should be way easier to solve, well, was solved by only one of those 6. So these 6, being able to solve problem 6, are very smart, but problem 2 wasn't solved except by Lisa and with some progress by Jack and Lynn. Okay. Going towards the average student, so if we consider the average score, which are some rationals presented above, but to make it easier, I took a random participant to have like integers. We notice that on problem 1, they actually got a better score on problem 3, which is usually the harder one, than problem 2. So something was weird that year. Okay. So, of course, before presenting the solution, I should present you the problem statement, which is longer than any slide I usually present. But let's give you some time to really digest, even while we will go through it like part by part. People who would ever watch this on YouTube can, of course, just stop the screen if it goes too fast. So it's about a finite set of points in the plane, and no 3 of them are collinear. That's an important property for the remaining of the question. So a windmill is something that's happening where like a line is moving, and initially the line goes through exactly one of those points. Next to it, it rotates clockwise till it meets a next point, after which the windmill changes its pivot, so it goes through this point, it goes through the next point, and this repeats. Now, the importance of the question is to prove that we can choose our line and our initial point, the pivot, in such a way that if this windmill goes on, goes on, goes on, visits every vertex infinitely many times. So it's quite a long question, so let's look to an example, really easy, starting with the definition. So we have a finite set of at least 2 points, where no 3 of them are collinear in the plane. So for example, here you see already 3 points. In the process, we had to start with a line through some point P, so we have chosen P, take now line L and we will move it. So it rotates clockwise. So softly it's moving on till it reaches a new point, Q. At this point, at this moment, the pivot changes. So instead of rotating through P, in which case the windmill would be pretty boring, just like a real one, we go through Q. So it goes on, moves through Q till it reaches the next point, which is called R here, and this goes on. This goes on forever. And so if you see the process of the windmill here with only 3 points, which were a regular triangle, like you just can repeat this. So it goes through the first point, meets the second point, keeps rotating, meets the third point, goes on, meets the first one, and repeats. So clearly, all 3 points have been visited infinitely many times. So we have solved the case for n equals 3. So if the problem is now clear to all of you, we can really focus on the core of the problem. So it's really proving that for whatever the finite set of points, so that there are now 3 collinears, since otherwise we won't know what's the unique point Q, that we can choose a point and a line through that point, so that this process, this windmill, goes through every point infinitely many times. So we need a proof in general. So for n equals 3, we already have seen no matter which point we choose, whatever line, it will work. Like, that's the idea, since you cannot have the process with only 2 points. And actually, this generalizes to if all the points would form a convex set, since then you just can take a line which is completely outside the convex hull, except from that one point you start with. If it rotates, it goes along all sides of your convex polygon formed by the convex hull of these points, and you visit everything. But those are just very structured examples, so that's not the general case. So for that reason, well, we will need to check also harder cases, but we can actually observe that no matter which line through a fixed point you take, it works with a regular n-hon. So here drawn with n equals 5. So in this pentagon, no matter which line you started with, the windmill will look different, but every point is visited infinitely many times. And you can actually check that after rotating 72 degrees in this case, you have the same configuration, except that you rotated it by 72 degrees. You have the symmetry, so all points are visited. So of course, if we have an easy case like this, there is not much to do. But it's about general. So we need to check for harder cases. So for example, to still have a small example, we can check to 4 points. If we have 4 points, either it forms a convex set, and then we already know we are done, or it's not. In that case, like the convex hull here is a triangle, again, taken regular, but the idea is the same for other triangles, being the convex hull. If we start from a line outside this triangle, if it rotates, it will visit the 3 points of the convex hull, but never reach the central point. So this is already a first case where we have to choose our P and L more properly. So for example, when we take a line through the center, this one works. So you can figure it out. So also for n equals 4, with a little bit of work, we already understand the question and it's solved. But it's really about the general case. So that's much, much harder. For that, we need to consider some other examples. So for example, for n equals 6, you draw a few points, a little bit more random, start with a few points. If you take it at the convex hull, it doesn't work. You try something else, you try other ones, you try to observe patterns, and you check for really interesting configurations. So for example, instead of just having a regular n-hon, we could have one additional point being the center. And in this case, we actually have almost the opposite as with the regular n-hon. So here you see a regular 9-hon with 1 point inside. So we have a finite set, it only has 10 points, and we can draw multiple lines. So some of them have been presented in dashed lines, but all of those do not work. the blue one works. So it implies this is a set where you cannot really choose L at random. So we have to be more careful. On the other hand, you can observe that if a windmill visits every point infinitely many times, actually the starting point doesn't matter. So in that sense, like the windmill need to be possible to be discovered from wherever you start. When you start in the center, it's pretty symmetric, so it doesn't matter. So it's exactly the vertices at the outside that matter. So we see already a configuration where like the choice of L is important. So by trying multiple of the important examples and also brainstorming about the general case, you can get ideas. So if you have ideas, you have solved 3, 4, 5, 6, but maybe that already involved 10 cases. It's not elegant for the general case. And if you suddenly generalize to the general, like you don't know how large n is, like you are not finished. So you really need some intuition about like how to do this based on the examples you have seen. So you observe from the solutions maybe some heuristics, like the line has to be somewhat in the middle, but that's a pretty vague statement, so we will have to make it more formal. So we can make the observations like we can start in whatever point, if it helps. And we observe that quite often in the non-trivial cases, like with the convex set, actually the line has to be somewhat in the middle, since if that's not the case, like it will fail. But there is the property, take a line somewhat in the middle would be very badly formulated, so we will have to quantify this and give a precise proof. So there is some challenge in having intuitive ideas about how to solve a problem and really give the proof. Since quite often, like with this problem, if you see the solution, it's easy to understand the solution, but it's about the whole process of understanding it and discovering it yourself. And that's a big challenge, and that's actually the special thing about this problem. Okay. So another observation is, while the process is going on, you can actually notice, for example, in the regular case with 1 point in the center, that the number of points on the left and the right, whatever left and right means at this moment, is roughly the same all the time. So that's something, like if that's an ID, that needs to be quantified. So in that case, like with other mathematical Olympiads in general, it can be good to state claims or lemmas and prove those. So for example, without having the whole solution, we can already start with our first observation and formalize it in a lemma. So whatever line and point we start with, during the process, if we construct a half plane which is fixed to the line, the number of points in that half plane will always be the same up to 1, because we have the moment that 2 points are on the line. And the proof for this is actually also rather simple if you just observe what the windmill is doing. So the half plane here is presented with an arc towards one of the two sides, so that left is made formal. It's just the direction of blue, right, the other one. Okay. We have the windmill. It moves. It rotates around our point P till, for the first time in the center presented, it meets another point. So this implies that on the left, there is 1 point less. So we went from x points to x minus 1. But after this, Q and P switch the property of being the pivot, and since the windmill goes on clockwise, no matter which side compared to P, Q is, like P will be again on the same side. So from x we went to x minus 1 to x after one change. But this one change is arbitrary, so this goes on. So at every moment, the half plane contains x or x minus 1 points. So that's might be an important observation to know what do we mean with the central line, it will be the one for which that the number of points on the left and the right are equal or equal up to 1. And then we know this is kind of an invariant. It's not completely an invariant due to this change of 1, but we actually notice an almost invariant, which is really handy. Okay. So at this point, the crucial idea is that the number of points on both sides is roughly the same. If we really take it in the middle while the line rotates, we hope, since in the examples we have studied, so it's really about the IMO, you have 4 hours and a half, you check multiple examples in this case to check what's true, what's not true, so that if you conjecture something, you have the feeling something is true. If it wouldn't be, you already would have like a trivial counterexample. So we want to finish the proof, and so think about this if it can be extended. So we observe that like either like the number of points is odd, so in that case we can take an arbitrary point and draw a line through it which ensures that both half planes have exactly the same number of points. If n is even, we can find a line which goes through 2 points, which splits into 2 half planes with the same number of points. So at that point, we are really in the middle. During the process, we have this change of 1. And actually, if you check, the line rotates. So at some point, it has rotated 180 degrees. So if it didn't visit all points, at some point, left and right kind of swept. But it didn't visit a point. So what would have happened is, we have a point which never is on L during this process. But the half planes divide the points equally. So if we start with L being exactly in the middle, either through 1 point or through 2, it rotates for 180 degrees. It missed P. It implies that it somewhat circled around P. But in both cases, the half planes have roughly the same number of points. But we see that for L, like the point that's the pivot of L prime is not in blue. And in the other case, there are 2 of them. So you have all the points on the left. This is half of them. So blue compared with L. And you have all the ones on the left, which is given by the blue arrow compared to the other line, L prime, and both of these roughly contain half of the points. But you have P and 3 pivots in between. So then it's simple counting to conclude this could not happen. So actually that finalizes the proof. So are there any questions about the idea? Since it's really the core of the proof, so like the proof or like the process starts with really figuring out examples, which ones are easy, which ones are hard, why they are hard, since if there is only one line essentially which solves it, it gives a lot of information. We observe things in a local move of the windmill and we start to formalize it. And then the real proof is about once we have this invariant lemma and we have the construction of L, which can be drawn from any point, we need to conclude. So we have the line L, which divides the 2 half planes with equally many points. It rotates. After 180 degrees, it becomes L accent, L prime. On both sides, there should be equally many points, and we have those 4, at least we are in the middle, so we get a contradiction. And so that's the core of like a very hard problem, as we have seen on the scores of the IMO. So the real big thing here is that an easy problem doesn't imply, like with an easy proof, it's not necessarily an easy question. So you notice problem 3 was at the end easier than problem 2, despite that problem 3 had a harder proof than problem 2. So that's especially implying that like leaders and instructors, when they choose problems from a short list, order them, it's a hard question actually to estimate. Okay. So at this point, we actually saw the solution of the windmill problem, and I could have stopped, but I want to think a little bit broader and give you another example on which you can think of it. So in this case, we have again some points in the plane, in white ones, in black ones, and we want to connect them with line segments which are not intersecting. Okay. So possibly, like we are 14 years later and we have seen how they solved the windmill problem, that's the way to go. If this is a hard problem, we have seen a strategy. Okay. But please try yourself. Okay. But we will soon go on. So people with YouTube can pause. Okay. So again, we can represent the points to just visualize it. So we have, for example, 4 black ones, 4 white ones. We need to connect them. So the idea of the windmill problem is really rotating a line so that we can do something. So in this case, what we could do is take an additional point, take a line through it, move it till the moment there are equally many black and white ones on both sides. If we now connect the lower vertices or points with each other and the upper ones, these lines won't intersect each other. So we immediately get an idea for a proof with induction. So you prove it with n equals 1. Everyone can do that. If you have 1 black point, 1 white point, you can connect them so that the one line is not intersecting with any other line. For n larger than 1, you draw an additional point, red line through it, split it equally, or at least like equally many black and white at the lower part and on the other side, and you apply induction and it works. Okay. Okay, and then you make it rigorous. So the ideas I presented, is it sufficient for 7 out of 7 for solving this problem? Like any student want to be like the coordinator for my solution presented here, like.
No clear about colors. Well, how you use equations that it doesn't figure out the colors of the points. What is the equation?
Oh. Okay, so you needed to connect a white with a black point so that those lines are non-intersecting, and so the red line should also like split black and white equally. And if you rotate 180 degrees, color swap. So if you take the difference, you choose the additional blue point not collinear with 2 others, at some point this is possible to have like equally many on both sides. So if I tell you, okay, like, so the proof, n equals 1, we can connect the white and the black one, that works out. N larger than 1, I will take a blue point, take a red line through it, rotate it, consider the number of white minus the number of black on one side, while forming a new windmill through blue. The difference of points can only go by 180 degrees, the sign is swapped, so at some point it's 0. So I can apply induction. No.
Doesn't this show that you can only jump from n to 2n? You should do one more step for the induction, right?
For the induction, you need to have it done for 1 up to n minus 1. That was the...
1, 2.
And since you choose the point not collinear with any 2 others, the windmill will be kind of continuous with changing one at a time. Oh. Okay. Can anyone make a final call? Good, accept, reject? Minor revision? Caesar, someone?
Maybe equality applies only with all points.
Indeed. Thank you. So the main issue is, it might happen you have a different configuration. If you rotate the line, at the moment that both on left and on right there are equally many white and black ones, you essentially have like the line where like on one side there are no points, so it's 0, 0, and on the other side it's n, n. So you cannot apply induction on n since you only know the conclusion up to n minus 1. So there was one final tweak. Your additional point has to be within, for example, a triangle spanned by 3 points, or in general, just in the convex set of all the 2 endpoints. Since in that case, if you find a line which has the property, because the blue point is in the convex set of the other side, like on both sides we have some points. So then we really can apply induction. And so in this case, we got a proof from the question. But it's not necessarily the most efficient. So having seen more solutions, so we have seen the solution for problem 2011 of the IMO, we understood that and we applied it here. We didn't actually solve this problem in a good way, even while it's a correct problem, because it could be done more efficient. The audience, no? Okay. Yeah. I thought someone from the audience noticed how to solve it. Okay, yeah, it's no, indeed. So the easier solution is you consider all possible matchings between white and black points, and you consider the one for which the total sum of distances is minimal. If in that case, like that matching would result in line segments which intersect each other like those, then we can observe that with a switch, essentially by the triangle inequality, we make it shorter. So this was not a solution. So by understanding what's really going on with a particular problem, we can come up with a more elegant solution. Since it's not generally about knowing the most, but about being the best to solve that particular problem. So you try to understand the particular problem, understand what's happening, and then come up with the best solution for that one. So with that, I want to conclude. So quite often you get a new problem. It's really about working out some cases to really have an understanding, get some intuition, and once you have the intuition, you try to formalize some lemmas, and with these lemmas to really get the proof. Okay. And with that, I thank you for your attention. I hope all of you can be creative at any competition.
All right. Thank you, Stijn, for this great talk. So if you have any questions for a couple of minutes, please. Oh.
Why in the second task we couldn't just shift the line parallel to itself? Not to rotate about the point, but just shifting. This way we for sure not for sure, but maybe it wouldn't work with some case of induction.
It's about the windmill process itself, like why the question is formulated that way?
Yes, why couldn't we just shifting line, not rotate?
So, yeah, the
To
question
achieve the
changes
induction.
completely. Since yeah, if you just would go up and down, you visit all points, or it bounces back and forth. So it's yeah, like it's J.F. Smith who made the problem and really found this nice thing. If you just shift up and down, you get something completely different. So that's just the problem statement. In the solution, you can fix a particular direction and move it. So like how to construct L and P, you can fix the direction of L, move this one parallel till it meets a point for which it's balanced. Like that can be part of the solution. I hope that answers the question.
All right, other questions, please. Do you have other questions? You can raise your hand. Don't be shy. Questions? Okay, if there are no more questions, let's thank our speaker again.
Thank all of you.